I know that we are summoning our lion, our bear, our dragon. Yesterday, I was listening to someone being interviewed, and they gave a phenomenal situation that I think definitely applies to what we've been talking about. I don't know if any of you are familiar with the show Dirty Jobs. Yeah, and the host, Mike Rowe. So, Abby, can you kind of share for those who aren't familiar with the show?
I like the newer ones that they've made. It's just so like different jobs aren't like conventionally like desirable, I guess.
You know what we would think of dirty jobs, and so yeah, you probably end up in the shower when you get home for so many different reasons, and it's not necessarily dirt that you're involved with. You might be working on the inside of a wind turbine and you get some grease on you, or it's just, just unconventional situations. Well, probably about, I can't remember what season it was, but it was, I'd say maybe the 4th season. They talked about that before that, they go to the wind turbine location, or they go to the water treatment plant, or they go to the leather producing factory. And what they always get, Mike Rowe and his crew, is a safety talk. And they were immaculate as far as their accidents and injuries the first 3 seasons. But then come the 4th season, they started to have falls and break bones. And they were just wondering, what? We're paying attention to the safety kind of guidelines. What is going on? And their assessment was this: we've been told so many times the same regulations that we're forgetting that we ourselves are really accountable for our own safety. So we're hearing okay, be careful where you step, but we're not really saying, okay, I need to be careful where I step, and so on. So they followed up with this person that was being interviewed, this excellent, real data-driven conclusion. So we know when we're at an intersection, if you are walking, you can wait for a sign to tell you to walk or not, yeah? Well, not all intersections have those. Do you know where they have those walk and don't walk signs? There are way more pedestrians that get injured than if you yourself have to say, is it safe to cross? So it's about being accountable for you, yeah? Or expecting somebody else to take care of you. And it depends on the situation, yeah? But as far as we are concerned with our learning, we are taking the control. We are the lions or the dragons or the bears. And as cheesy as that is, it really is true. So let's show that nature today as we master gas stoichiometry. Comments, questions, concerns? All right. So gas stoichiometry, we did 3 examples yesterday. So to remind us, if you are given a species that's a gas, either reactant or product, and we're asked to find another gas, reactant or product, the coefficients can be volume ratios. That's what we learned from that, yeah? Coefficients can be volume ratios. Okay, so that was, the takeaway from that. Okay, then next, when you are at STP with gases, we can use molar volume whenever we need it. We know how integral moles are to stoichiometry. So whenever we're working with gases, we can get into volume from moles or into moles from volume, as long as we're at STP. So kind of the situation that poses a little more work is when we're not at STP. And we saw yesterday that if we start in terms of a solid, so if we, are given is not a gas. Well, And it's not in any way, shape, or form that I would ask us to like memorize steps or know their steps. I mean, just start problem solving and then see where you go. If our given is not a gas, so that means we're going to begin, I betcha, with the mass of a solid. Well, then we saw yesterday that we're going to start with the stoichiometry. So that's what we do first. If the given is not a gas, so this would be like, I don't know, scenario 1. We call it A. The given is not a gas. We do the stoic, and this is where you decide, bless you. Are you team combined gas law, or you team 22.414 or team ideal gas law? So you do the stoic, and then we have to employ a gas law. And again, it's either combined or the ideal gas law. And you choose, and we will practice today so you can really get certain with which path you want to go. Well, what I'd like to start with today is the problem that we got the reaction for. Well, what if our given is a gas, but we're not at STP? And so we'll be beginning with the volume of a gas. Okay. What I would like to do is 1 together. Remember I said we're going to do 4 together to really be exposed to the learning of the 4 different types that will come our way. So this was 1, 2, 3. Now we're on to the 4th one. Then it'll be turned over to you to practice all of these to just get more certain with it. Okay, so page 12 of your packet, example 6. Any questions before we dig in? All right, so we came up with this reaction yesterday. Remember, when we react alkali metal with water, we get the metal hydroxide and H2. Okay, so we want to produce 400 milliliters of hydrogen. We're not at STP. You know, you don't have to write down givens. I'm just going to go ahead and place them here. And we're asked how many grams of sodium. Okay, Troy, what would you do first, sir? What is your kind of problem-solving talent tell you? So, are you team combined gas law and molar volume? Totally fine. So, you are saying, all right, let's do molar volume, but we could also be team ideal gas law. So I'll show us that way. Okay, so you're saying get that to be at STP. Why? Exactly. And we know we need moles to be able to do stoichiometry. Oh, very good, very good, very good. Maybe we need to reverse roles. You could be at the document camera and I'll take your seat. You know exactly what to do. So first, combined gas law. Solving for volume at STP, so then we can use molar volume. All right. Oh. Goodness gracious. And I get 334 milliliters. Now, I can't help but suggest to us that whenever we're employing a gas law, we should just make sure we ask, okay, are we putting in things about a gas? And of course, hydrogen is. You can't use gas laws with solids or liquids. Okay, so this is how many milliliters of hydrogen we have. Okay, yippee. This is at STP. So now I can begin my stoich with the 334 milliliters of hydrogen. All right. We're using molar volume. I need to get into liters. And I know every 22.414 liters at STP is 1 mole of the gas. Troy, where do I go from here? Excellent. And then? Oh, phenomenal. What do you get for your answer, sir? Very good. Yes. Because of the 720. You are so right. Oh, Caitlin, thank you. Thank you. Thank you. So how does then our answer? Is it 0.69 or let me see. Oh, yeah. Oh, no, 0.68. Do you agree, Caitlin? Okay. Are we okay with the setup? Anyone have a question? Well, what if you'd like to do the ideal gas law? We're not at STP, but no worries. In comes the fairy godmother equation. So PV equals nRT. We're starting with gas. What is the difficulty? We need moles of the gas. We have the pressure, we have the volume, we have the temperature. So we will solve PV equals nRT for N. Be careful rearranging. PV over RT. Now, of course, the only thing here, we have to make sure that we are in the units that are required because of R. So we have to convert this to atmospheres. And our volume has to be in liters. So I'll just do the converting within the equation and then R per Kelvin mole times the temperature. All right. All right, we get 0.015 moles of H2. And I can't help but just ask myself, okay, H2 is a gas, right? I just used the ideal gas law with the gas. I'm good to go. Now we do our stoich. So I found moles of gas. I can go right to the mole ratio. And for every 1 mole of sodium, 22.99 grams. And yep, so we do get a varying of the 100th place, but because of rounding and so on, we're good. Okay, so you choose which path and you can alternate. So if we go back to, if we do want to be sketching down, so if our given is a gas, the first thing we have to take care of is the gas law. So do you use the combine to get yourself to STP, and then you can use molar volume, or ideal gas law, and then you're solving for moles? Then you do the stoichiometry. Yes?
So on our last problem, can we go back to it?
I absolutely will, sir. Okay, and I did take away this. I'll go back to the page that I just had up. Go ahead, Max. What is your question, sir?
So why for the volume at the top, like putting 1/8
Okay, in the ideal gas law, there's definitely criteria for either way that you choose, if you use the combined gas law or use the ideal gas law. Okay, so kind of like the curveball with molar volume is, to use this, we have to be at STP. So that's why we had to do that first step if you're going the route of molar volume. Okay, well, the kind of curveball with the fairy godmother equation, which I call the fairy godmother equation because it doesn't matter if we're at STP or not, it flies in to save the day. However, we have to accommodate the units that are on our gas law constant. If we are plugging in a pressure, but we're looking for volume, we need something to cancel the unit of pressure. So it has to be in atmospheres, and our volume has to be in liters. So I just showed the conversion, how I would take the given pressure and get it to atmospheres. Well, I would divide by 760. You don't have to show me that. You could do it on the side and then plug in atmospheres. I just thought I would show us like in the equation.
Okay.
Is that like bamboozling, or that's okay?
Yeah.
Okay. Are you sure?
Yeah. Like you have to cancel out on the
Yeah, and doing this because I was given my pressure in millimeters of mercury, but the gas law constant has pressure in atmospheres. So when I divide this, this will be in atmospheres, and then this will cancel. Correct. Other concerns? We get good at this through practicing. So you have the 4 examples to look back at, and I am here. I'll be walking around to take a look at your work. If we could go to page 14, please. Page 14. All right. I'd like us to do 4 of these, and I will, right up front, share the answers. If we could tackle the ones that I have underlined, and let's see, our answer for 2 is 15,000 liters of ammonia. Ugh, 2 sig figs, but that's because of that 45,000 and the 550 degrees Celsius. The answer to 3 is 42.4 grams of carbon. The answer to 4, 7.44 liters of O2, and 5, 0.0774 liters of, grams of lithium, 0.0774 grams of lithium. Okay. If you want to be problem solving here, you can also help yourself to paper. Let me know what we need. The only one at STP is number 5. So this will get us good at knowing and practicing our different methods. All right. If you want to work with your neighbor, if you want to work with your lab partner, if you would rather work at your lab bench, but we want to tackle these. Okay, go team.